No questions? All right. So what were we talking about? We were talking about heat capacity of any general molecule or material. And we started to think about coming up with models that can explain how would the heat capacity vary with temperature. The first model that we looked at was to consider any given molecule made up as atoms vibrating around their equilibrium position as per a harmonic potential. So not too long, not too large vibrations, short vibrations. If the vibrations are short, anything can be represented as a harmonic potential. And there we found, so we are talking about heat capacity versus temperature. So classical harmonic oscillators model, classical HO, gave us CV is equal to 3nk at all t. And that was quite bad because we know we can expect that at zero temperature, the heat capacity must go to zero because you have quantization. You cannot just excite things to the next, from ground state to the excited state. There will be a certain barrier that you just cannot cross if the temperature is small enough. Then we went to a quantum harmonic oscillator model. Here we have to account for the density of states of frequencies. What possible frequencies are there? So this frequency could come from Einstein. And there we got something that goes to CV is equal to 3nk at high t. And CV is proportional to e to the power minus theta e by t at low t with some parameters, and it's proportional to that. So it dies down exponentially. So it dies down too quickly. It goes to zero, but too quickly. Today, the model we are going to look at assumes a different expression for the density of state. It's called Debye's formula. Debye came and said that, well, I don't know what was the order. Maybe Debye did it in parallel to Einstein. I don't know. But I think he came after that. So Debye said that, so what is the physical picture here? The physical picture is that we are talking about every atom has three independent directions, right? So X, Y, and Z. And each of these we are treating as a separate harmonic oscillator. This is a harmonic oscillator, this is a harmonic oscillator, this is a harmonic oscillator. They are all independent. They have their own frequencies. What we don't know is what are these frequencies. So Einstein came and said that, well, I'm just going to assume that the frequency is a delta function at omega Einstein. Okay. So we are talking about here, we are talking about G of omega. So Einstein said that all atoms in all directions have the same frequency. That's clearly not true, right? Molecules have directionality. Not everything is something where everything, every direction, every atom just vibrates with the same frequency. Clearly, this is a very, very abrupt or aggressive assumption. So Debye said, well, hold on, that's not really true. There will be smaller frequencies, there will be larger frequencies. There should be a distribution of frequencies in a material, not just one unique frequency. So Debye said, no, I don't know how he addressed Einstein. This is German. So Professor Dr. Einstein, there should be a distribution of frequencies. So let's think about what this distribution might be. Is there a largest frequency that a material can have? Can you think that this distribution of frequencies, whatever this G of omega for Debye should look like, can it be can it go up to any value? Can debye give you a frequency that happens at as large a value as possible? Is that fair to say that a material, any molecule, can be made up of atoms vibrating with a frequency that can be arbitrarily high? What do you all think? Or should there be a cutoff beyond which we have no frequencies? Any idea?
Well, there should be a limit, because if we allow them to vibrate as much as they want, then like the material will break down, right?
Correct. You are in the right direction, Kishler, but can you try to be more quantitative? How can we quantify this? Where is this coming from?
So they should be at some if we are talking about molecules, we should make sure that their vibrations should be like that, so that they don't break the bonds.
Yeah, so that's correct. So what Kishler is hinting at is basically that the frequency omega is kind of proportional to 1 over lambda, the wavelength, right? Anytime you have a wave with a certain frequency, higher frequency means longer wavelength. And we know that there is a minimum wavelength that any material can have that corresponds to the bond length, for example, or corresponds to the lattice spacing, right? If you're thinking about a crystal, then the lattice spacing A, or bond length, you know what are the bond tends to be around 10 bonds tend to be around 2 angstrom or something like that. You cannot really vibrate with a frequency that gives you a wavelength. So higher frequency means shorter wavelength. And you cannot have a wavelength which is shorter than the typical interatomic spacing. So there is a cutoff. And that cutoff we are going to call omega d. Okay. Now, I don't know whether omega d should be more than omega e or it should be less than omega e. I think this is a parameter, so there is no reason to really worry about it. So we know that beyond this, the density of state should be zero. That's one assumption in debye, that at omega it's sharp. In reality, it might not even be that sharp. Maybe there is fluctuation. So debye said that the distribution should look something like this. It should be proportional to omega square for omega less than equal to omega d, and zero for omega more than omega d. So here, this is Einstein, and this is debye. Why the omega square? I'm not going to go into deriving omega square, but it basically comes from theory of solids. It comes from treating a material as a homogeneous elastic medium. So you have to do your mechanics. By mechanics, I don't mean classical mechanics, but mechanical engineering type mechanics, and think about where does it come from. So, but the key aspects you can see already. You can see that beyond a cutoff, it should be zero, because we know there is a minimum wavelength that a material can have, and it goes to zero. There is no vibration with zero frequency. So I can, if anyone wants, I can give you the full proof of why g of omega goes as omega square, but this is the final expression that comes out. We are going to use this. If you have a similar problem in exam or homework, I will give you such an expression. But the key thing to keep in mind here is that it is proportional to omega square for omega less than omega d, and it is zero for omega more than omega d. And this proportionality constant is related to the volume of the material and the speed of sound in the material. So Cs is equal to speed of sound in that material or in that molecule. So this is Debye's formula. And I think, so ask me if you want its derivation. It will take us far away from statistical mechanics, even further away from chemistry in order to do that. But it's not too hard to imagine that it goes to zero, that's obvious, and it's proportional to omega squared. That's the message here. So can we calculate omega d given this information? Any idea? How should we go about calculating omega d in terms of these constants written over here? Is there an equation that we could use?
You know the integral of GW should be 3n.
Exactly. Nathan is absolutely correct. Thanks, Nathan. So we know that the number of oscillators should be 3n. So we can do this integral. So we can say now that therefore 0 to n. So we know that this integral should be equal to 3n. Therefore, we know 3v by 2 pi square cs cube omega square. And this thing goes up to omega d, because apart from that, it is 0. So this gives us that omega d, the Debye frequency, is equal to speed of sound multiplied by 6 pi square density of the material n over v divided by 1 by 3. And this makes sense. If the material is denser, the cutoff is larger. You can have higher frequency permissible if the because the material is packed together, the lattice spacing is tighter. So it makes sense what we have over here. And yeah, so this is the Debye frequency that we can calculate given this formula. But where does this take us? Does it get us to the excuse me, does it take us to the T-cube dependence, the elusive T-cube dependence that people had seen in experiments, but theory was not able to explain? So for the T-cube dependence, if you want to forget the value of this constant, if you want to forget the value of omega d, that's all okay. All you need to remember is that Debye has a density of state that is proportional to omega square. We will just proceed from there. So how do we go from this? So recall last time, and you can look this up in your notes, we derived a very general expression which was before Einstein or Debye. We showed that ln q is equal to minus 0 to infinity d of omega g of omega ln of e to the power beta h cut omega by 2 minus e to the power minus beta h cut omega by 2. This was derived on Thursday. We showed this. So let's work with this. Let's simplify this a bit more, and then we will plug our equation. So this is equal to minus 0 to infinity d of omega g of omega ln e to the power beta h cut omega by 2 multiplied by 1 minus e to the power minus beta h cut omega, right? So now it's a ln of product, so it becomes, so this is a product, so this can be brought outside the ln and it becomes a sum of ln's. Ln of e to the power beta h cut omega by 2 is simply beta h cut omega by 2. So the first integral becomes minus 0 to infinity t of omega g of omega beta h cut omega by 2. And the second integral stays 0 to infinity d of omega g of omega ln 1 minus e to the power minus beta h cut omega. Okay. So this is ln q. We are not really interested in ln q. We are interested in CV. CV will come from partial E bar by partial T, and E bar can come from minus partial ln q by partial beta. So what we are really interested in is taking, so let's call this as, let's call the Debye frequency as equation number 1, this as equation number 2, omega d as equation number 3, and this one as equation number 4. So what we are really interested in is taking equation 4 and differentiating it with respect to beta. Okay, so let's do that. So for that, let me mark my page numbers. So we go to page number 3 and we write down E bar is equal to minus partial ln q by partial beta. And if you do that in the first one, it's simple. This has no beta, this has no beta. And this is kind of interesting. This is something which might confuse you later. The g of omega, the density of state, you might ask, why doesn't the density of state not depend on temperature? That's a very good question, but that's the way we have defined it, that it is a temperature independent property. The density of the probability of possible frequencies is temperature dependent. Now, every frequency, if you think of the quantum model, has ground state and excited energy states associated with it, right? For any omega, you have the ground state at half h cut omega, then you have the first excited state at 3/2 h cut omega. And which excited state do you lie in? That is designed by the temperature. But the distribution of the frequencies themselves, that is independent of temperature. And that's kind of subtle fact. So when we differentiate this, I didn't mean to erase it. The only term that is dependent on beta is here is this one. And in this one, it's inside the log of this. Okay, so let's do that differentiation. And it's quite easy. What we get is 0 to infinity d of omega, g of omega, no beta now, h cut omega by 2. And then this second term, 0 to infinity d of omega, g of omega, h cut omega, e to the power beta h cut omega minus 1. Why did e to the power beta h cut omega go in the denominator? Because it was a ln, and I did a couple of, just one more I multiplied and divided it by e to the power minus beta h cut omega, e to the power plus beta h cut omega in the top and bottom. So if 4 to 5 is algebra, simple algebra, it's not too bad. Okay, so we have our E bar, and now we need to talk about CV. That's what we are really interested in. So we are almost there. And remember, this is all quite general. This has nothing to do with dy. We haven't put in yet the value of g of omega. So CV is going to be partial E bar by partial t, which is the same as minus k beta square. K is Boltzmann constant. Partial E bar by partial beta. This is a manipulation you will be using, you have used, and you will be using many, many times. So now, therefore, equation 5 implies that we have to differentiate with respect to beta. That's wonderful, because this one has no dependence on beta. So we can just ignore it. The only dependence on beta comes from this second part. And in the second part also, it comes only from the denominator. So it's not that bad. Even though I'm writing everything, if you go and do it, it's really simple algebra. It's not complicated. So what I'm going to do here is, and especially since there is no homework which is due for until 23rd, it's a good idea for you to work through these steps and do it yourself so everything is consistent. It might look just like math, but when you work through the steps, you will realize, wait, why did they not do that? For example, typically every year someone asks me, why did you not differentiate g of omega with respect to beta? How do you know that? And that's a interesting question, you know, things like that. So work through the algebra, and what you get is CV is equal to k 0 to infinity d of omega e to the power beta h cut omega by e to the power beta h cut omega minus 1 whole square multiplied by beta h cut omega whole square g of omega. This we call equation 6. This is valid in general. We could have done this before Einstein expression. Why did we not do this? Because Einstein had a delta function. So it made life so easy that we didn't even bother to go through all this. We just stopped here. Now we can plug in Debye's expression. In 6, use equation 1, which is the g of omega for 1. So what will that do? That will lead to extremely horrible integrals. For example, this will become, first thing that will happen is we are no longer going till infinity. We are going till only omega d, right? Because g of omega goes to 0 beyond omega d. D of omega e to the power beta h cut omega by e to the power beta h cut omega minus 1 whole square, b to the power h cut omega whole square, and so I got e to the power beta square, and g of omega is 3v omega square by 2 pi square cs cube. I just wrote down the whole thing. So this is equation 7. This is valid only for Debye. Now we introduce a variable x, which we call beta h cut omega, because beta h cut omega shows everywhere, right? So why not call it x, just to simplify.
Excuse me?
Yeah.
So for equation 6, can you explain where does the beta h bar omega square come from? Because I only see yeah. I didn't quite follow like the beta h bar omega squared. That
I think
that,
it's correct. I mean, I could go through the whole algebra right now, but I think it's correct. The beta square, the beta square, first of all, comes from
oh, okay, yeah,
over here.
yeah. I saw it. Yeah. I saw it. Yeah, no problem.
This is textbook. It's just algebra. So, but do try it. It will be helpful. It will be helpful.
Yeah. I
If there
missed
was
the
any,
front part. Yeah,
yeah,
thanks.
if there was any physical or chemical concept in this part of the derivation, I would have done it in detail. But even if there was a useful mathematical trick like summing a geometric series or something like that, I would have showed you. But this is pure simple algebra, nothing else.
Yeah. I got it.
Good. No, it's good to ask if anything is not clear because I might have made a mistake. So with this, we get CV is equal to K 3V. And instead of trying to write all the constants, I will soon get to the final expression so we can look at it and see what's going on. 0 to beta h cut omega d e to the power x minus 1 whole square x to the power 4 dx. So we do if you plug in the value here of omega d, remember we haven't yet used the value of omega d. Omega d is equation 3. So use 3 in 8, and then you get something which is a lot of terms cancel out from numerator and denominator, and then you are left with CV is equal to 3nk multiplied by 3 divided by beta h cut omega d whole cube 0 to beta h cut omega d e to the power x to the power 4 by e to the power x minus 1 whole square dx. And this we call as 3nk Debye function fd as a function of theta d by t. Okay, and I will explain in the next page what that is. So this Debye function shows up a lot, and we just leave it in that name. And this is equation number 9. In equation 9, and again, if you have missed out on some of the algebra, don't worry, all the notes are online anyway. Try to see the picture that I'm trying to form. Notice where are the gaps mentally, and then go back and try to fill up the gaps. That's the most important thing here. So we have defined Debye function, which is fd of y is equal to 3 by y cube 0 to y e to the power x by e to the power x minus 1 whole square. So in the days before Wolfram alpha or computers, these integrals would show up in different aspects of physics or chemistry. Similar integrals would show up in number theory, in calculus, here and there. So people would have books called tables of integrals, and integrals would have names, and they would have given the values of these integrals, limiting values, this and that. So these names have existed for a very, very long time for that reason. Now you just put it in Wolfram alpha or your Mathematica and everything is done. And we also introduced theta d over here. So theta d, the Debye temperature, is defined as K theta d is h cut omega d. So instead of looking at the Debye frequency, we think of the Debye temperature. It's proportional to that, but you have just changed the units. So this is equation number 10. This is equation number 11. And once I finish this derivation, which is in 2 lines, then I will walk again from 1 to 11 and give you the full picture and mark which are the steps that you should go to finish. Okay, so the things about this Debye function is that as temperature goes much above the Debye temperature, as T becomes much larger than theta d. Let me actually write down the equation from last page because we are going to look at it. Let's remind us of equation 9. Equation 9 was CV is equal to 3nk fd theta d by t, and we have our formula for fd of y. So let's think about as t becomes much larger than theta d, what happens to the Debye function? What happens to Debye function of theta d by t? So what we are talking about is when t becomes very, very large, this function that we have written over here, does anyone know what value it might take? Is it obvious in any way? What happens to the limit of the integral? The y in the top over here, that goes to 0, right? Because you are integrating only up to a value that is getting smaller and smaller, but at the same time, this also goes to 0. So this integral goes to 1. And I'm feeling sad that I'm not doing this, but this is the point I have to remind myself that you all went through this in the first homework, so I shouldn't feel that sad. That is why I did it in the first homework. So you have seen this. You actually did this. Maybe you didn't call it Debye function then, but you actually saw this in the first homework. For t much smaller than theta d, we can say that theta d by t tends to infinity. So by the way, let me finish. If this happens, then CV tends to 3nk, right? Because all of this goes to 1. So we recover our high temperature limit. As theta d by t tends to infinity, then CV becomes approximately 3nk 3 by theta d by t whole cube 0 to infinity e to the power x to the power 4 dx by e to the power x minus 1 whole square. This is a beautiful integral. This integral shows up in a lot of nature, and it's just amazing because, believe it or not, it equals pi to the power 4 by 15. Exactly. That. Oh, sorry, I missed a 4. 4 pi to the power 4 by 15. Those of you who really like math can try to prove it. I think there are many ways of proving this. Pi is one of those constants which shows up in really random integrals, really random series. If I'm not wrong, there is a series for pi which looks something like 1 minus pi by 4 is equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus 1 by 9. I think this is correct, but maybe I'm wrong. It's just like, why would that be equal to pi? But it is. Maybe I'm wrong here, but it's something similar. So this series is pi to the power 4 by 15. People would play, there was an Indian mathematician, Ramanujan, who would derive series like this, and his proofs would be completely non-existent. He would just have intuition for why such a thing happened. I find these integrals very interesting, but we don't have to get into that much right now, but we get our main expression here. So the main idea here is that this is then 3nk pi to the power 4 by 15 multiplied by 3 divided by theta d cube, but proportional to t cube. We got our t cube dependence as temperature becomes much smaller. Debye model indeed does give us the t cube dependence. And you can, I want to give you a sense for this theta d for different materials or molecule, whatever you want to call it. NaCl has a theta d. You have to fit. How do you get a theta d, right? You get your CV at low temperature. Everything is known here, right? Number of atoms is known. Boltzmann constant is known. Pi is known. Temperature, well, you're fitting against it. So you can go and fit and get the value of theta d cube and thus theta d. So theta d in Kelvin for sodium chloride is around 308. Potassium chloride is around 230. silver is around 225, zinc is around 308, just to give you a sense of how these numbers look like. And this is the fitting parameter. There is nothing profound about it, but then if you have theta d, you can go to equation 11 and try to think about what is the omega d that you get out of it. You can play around with it and see, does it correspond to the bond separation or not? You can play around. So this is the end of phononic heat capacity. The next thing we are going to do is to talk about photonic heat capacity or blackbody radiation, not heat capacity, but what we have talked about is a gas made up of phonons. Next, we are going to talk about a gas made up of photons or blackbody radiation. Before doing that, let's go through what we did with Debye once again, okay? What we did so far today. So, and this is all one exercise in Chandler. So we took 2 lectures almost to do it. So we had our heat capacity versus temperature. We always assume atoms are oscillators. They could be classical, they could be quantum. When we do classical, we get a heat capacity which is true only at high temperature, 3 Nk. And that, if you, those of you who really like thermo should go and think this is a direct consequence of the equipartition theorem, which you study in PChem or in thermo, right? Equipartition tells us, you can derive this from equipartition, that heat capacity is 3 Nk. But classical mechanics stops there. It does not tell us anything else. And the reason being that we know that quantum mechanics must imply that heat capacity goes to 0 as 0 temperature because of the quantization of energy. So there we have to think of atoms made up as quantum harmonic oscillators. The question is, so 3n quantum harmonic oscillator, every atom has 3 independent directions. But the question is, what is the frequency of the harmonic oscillator? And that brings us to the notion of density of states, G of omega, this one over here. Einstein said, let's assume every atom in every direction vibrates with the same frequency, omega e. That made our life easy because that's a delta function. So this thing is delta of omega minus omega e multiplied by a normalization that comes from 3n, as Nathan remembered today, and maybe others also remember. So we get our proportionality constant. Debye said, well, that's not really true, and that's why your heat capacity falls down so quickly. With Einstein, the heat capacity dropped down exponentially in temperature, which is too fast. Experimentally, that's not known to be true. It behaves something as TQ. So Debye said that's not true. There will be a distribution of frequencies. And how do we calculate the distribution of frequencies? First, we say that, well, you cannot have a frequency higher than a cutoff because that is the bond length or the lattice spacing, something proportional to that. These two things are not really very different from each other, right? They're the same order of magnitude. So you have some cutoff. And before that, you use theory of elastic theory of solids. So you assume that every solid is like a rubber band which can move elastically, and you use that to calculate the frequency, and that's where the speed of sound comes up. But the omega square dependence is there. And I did not really explain why is it omega square, why is it not omega, why is it not omega cube. I just threw the omega square at you as a tool that we are borrowing from another field in order to get our understanding of heat capacity. Once we have this, we can go and calculate omega d by using the normalization of the density of states. And from that, we went and wrote down our expression for LNQ in general. We simplified it. We said, well, E bar is going to be minus partial LNQ by partial beta, and CV is going to be this thing. This is the point at which Jingchen, I think, got confused as to where does this come from. But again, there is some algebra here. Go and work through it. Maybe I made a mistake. Maybe Debye made a mistake. So please work through it. It's worth it, right? It's like buying a stock in Apple when it is an unknown company. It might become worth a lot. It might be worth nothing, but you should buy it. Maybe it will be worth a lot. So this is that type of derivation. If you find a mistake, it's wonderful. You prove Debye wrong, but most likely you won't. But in the process, you will improve your understanding. So that's good anyway. So we do a bunch more algebra. We introduce the Debye function, and we come up with an expression which behaves as 3Nk at very high temperature and proportional to T cube at low temperature as temperature tends to 0. And so from this, what we have shown is that CV is equal to AT cube at low temperature. Most materials follow it. Notice that, yeah, most materials follow it, but metals do not follow it that well. Here I just wrote the Debye function. I did not tell you how good is the quality of fit. So this AT cube comes from thinking only of phonons or lattice vibrations. Phonons are just another name for lattice vibration. The reality is that a better fit comes from AT cubed plus BT, where the B comes from electron. And that's a very interesting proof. That will be like so currently we are doing applications of StatMech, right? So our first application is really looking at a gas made of phonons, a phonon gas, or heat capacity due to lattice vibrations. Later, we will be looking at a gas made of electrons, which is extremely important. And there we will see that we don't get a T-cube dependence, we get a linear temperature dependence. And this is actually very powerful at low temperatures. So any questions before we move on to black body radiation? So in this derivation, Chandler won't be of much help to you. So because he just gives it as a homework problem, which is a bit mean of him. So you have to go and fill in the blanks. So we just, in case there are no questions, you can ask me later. We just finished application 1 of StatMech, which is phonon gas and related heat capacity. I won't just call it all heat capacity because, as I mentioned, later we will have electronic heat capacity, because when you pump heat into a material, it doesn't just go into making the vibration stronger of atoms around their mean. It also might excite electrons. If you have a Fermi level, electrons can move above that. In fact, when I was an undergrad, and my undergraduate degree is actually in something called metallurgical engineering, which is very engineering, it's old school material science, but we had a very solid state physics bent in that course. And one of the ways we would define a metal is not like something which is shiny or you can beat someone else with, it's very strong, this and that. We would say a metal is a material with a Fermi surface. So for metals, this AT cube does not work out. You have a BT dependence, and we'll get to that later. So we just finished this application 1. Now we are going to look at application 2, which is really interesting, I think, and it's a gas of photons. What do I mean by gas of photons? By gas of photons, I mean an electromagnetic field in thermal equilibrium. So here also we are going to have oscillators, but a few things will be slightly different. In thermal equilibrium with its container. It is also called black body radiation. And so the best way of making it is to take a material and some material and make a cavity in a large piece of material. Evacuate the cavity. And let's say the cavity has volume V. Heat the material. So step 1, step 2, step 3. Heat the material to temperature T. So this is our material. And then once you heat it to temperature T and you thermally insulate it over here, okay, nothing can be observed except through a very, very tiny hole. This very tiny hole, you can see what's going on, okay, inside the material. Otherwise it becomes NVE and you cannot really observe anything, right? So this is a very tiny hole, the tiniest hole you can imagine. And then you heat it at material T until equilibrium is established, and you just allow the tiniest observation that you can make. If you couldn't make the tiny hole, then you can't observe anything. So it's kind of like cheating, make a tiny observation and see what's going on inside. So what will happen inside this is that the atoms of the wall of the cavity will be constantly absorbing and emitting radiation, right? Because, well, they are getting excited. They are doing all kinds of things. You have given it at a certain temperature. It's not at the ground state. And the question then is, what is the energy density of radiations at a certain frequency? Because I said they are constantly absorbing and emitting radiation. And the question is, how much? What is the frequency of this radiation? What is going on inside? This problem sounds very esoteric, but it's very fundamental. Does anyone, what is the most fundamental example of this you can think of a black body?
The sun.
Okay, let's go even further. I was thinking of the early universe, right? We are still observing it, right? So there was a cosmic background explorer experiment, so basically we are going to come up with a model which tell us the energy density associated with a certain frequency. This will depend on temperature, right? Because if the temperature at which we prepared this thing, like the sun, for example, is higher, then we would assume this energy density to look like a certain way. If it's at a lower temperature, we expect it to look like a certain another way. So this cosmic background explorer experiment looked at the radiation coming from the early days of the universe and used the expression that we are going to derive to fit to it. And it got the temperature of the early universe. I think it's something like 2 Kelvin or 4 Kelvin, but it got it within 10 or 12 decimal places by using the formula that we are going to derive now pretty much from scratch without making any assumptions. So it's super powerful for that reason. And yeah, so that's the simplest example you can think of. So here, so earlier in application 1, we looked at lattice vibration, right? And the quanta, we had quantum mechanics. And what was the quanta of lattice vibration? It was called phonon. In application 2, we are looking at electromagnetic vibration or EM vibration, and the quanta of electromagnetic vibration is photon. These are abstract concepts. 100 years ago, there were no photons, there was no quantization, none of this existed, which makes you wonder in the early 22nd century, when someone is teaching StatMech, will it have new things? What else would have happened? I don't know, kind of crazy. It's worth living to see what it looks like. So the idea here is that you have photons of energy n plus half h cut omega. This is why I told you to read up the quantum harmonic oscillator. You have quantization, and the energy for the quantum harmonic oscillator applies to whatever thing you are looking at. Lattice vibration, electromagnetic vibration is the same harmonic oscillator. That's why in quantum mechanics, some of you probably took Leah's class, and Leah probably started, Leah Dodson class, she started with that. Or in undergrad also, you must have done this. So, and we don't know what is the frequency. Furthermore, we don't know what is the value of n that frequency will take, right? So there is going to be a certain distribution of frequencies. And in that distribution of frequencies, for any given omega, you could be in ground state, you could be in excited state, and that's the idea over here. One very important thing to keep in mind here is, and this is related to one of the problems on the third homework, is that the walls are constantly emitting and absorbing photons. We cannot control their number. In a black body radiation, you cannot control it. So in chemistry, how do we control the number of something? When we went from canonical ensemble to grand canonical ensemble, we said, if we want to control the number, we will enforce a chemical potential, right? And matter moves, just like you could move from gravity, you could move from up to down. Matter moves from high chemical potential to low chemical potential, depending on what is the driving force or something like that. For photons, you cannot control this chemical potential. This means that if you were to use grand canonical ensemble, it's gonna be messy. You cannot control mu. So one way to solve this problem is to use grand canonical potential with a chemical potential of 0, because they can be arbitrarily created or destroyed. So we can use that with V and T, or we can use canonical ensemble. So this would be Z, or we can use canonical ensemble Q, and we will only think about V and T because N is arbitrary. We are not even going to think about it. It can vary depending on what is going inside the system. We are not going to consider it as a variable, and this will become cleaner as we go through the proof. If that bothers you as to why did we not consider N, then you can go and redo the whole thing in grand canonical by setting mu is equal to 0. Okay? So with this understanding that we are going to think about Q of V comma T, we are ready to set up a problem. Also, the other thing is we said that photons have energy n plus half h cut omega. So, and any number of photons can have the same omega. They can all get into any excited state. It doesn't matter. So photons are bosons. This is the term I introduced earlier. We haven't really looked at the properties of bosons, but this is something we have mentioned. So just to take note that later we will derive a general treatment of bosons and fermions, and what we are doing in this application will fall out of that. It will directly fall out of that. Okay. And so now we have to write down Q, the partition function. What is Q? We all know this. We go to every microstate and we sum e to the power minus beta E nu, right? So what is E nu going to be? E nu will be, so what does it mean to go to every microstate? And pay attention here, this is a bit subtle. This means going to frequency number 1, whatever that frequency is, thinking of what occupation number you have in that frequency. It could be 0 or it could be infinity, right? It could go to any level of excited state. Doing the same for frequency number 2, doing the state for frequency number 3, for as many frequencies as you can have. There is no limit here. So notice we are not constraining ourselves by those 3n oscillators thing here, right? For phonons had 3n oscillators, right? So we talked about the number of frequencies. We talked about the frequency corresponding to every oscillator. And then we switched to the frequency basis and life switched and life changed. Not here. Here we can make as many photons as we can, and they can be in any excited state. So this thing, I will just write dot, 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 because I don't know where it's going to end. Then I need to sum up the energy, and the energy will come from the, so N1 corresponds to frequency omega 1, N2 corresponds to frequency omega 2, N3 corresponds to frequency omega 3, so on and so forth, right? So here we have to write e to the power minus beta N1 epsilon 1 plus N2 epsilon 2 plus dot dot dot, where we have done two things. Firstly, we have introduced epsilon j as h cut omega j. So you can see in this formula, right? You could have written it as n plus half epsilon, right? So we have called, and then it would be n epsilon plus epsilon by 2. So we have introduced where epsilon j is equal to h cut omega j, and assume 0 point energy is 0. That's not a bad assumption. Why? Because everything else would just come out over here. It would just be a prefactor. It would not depend on the value of n1, n2, n3, right? The 0 point energy or ZPE will just be a prefactor. And why does that not matter? Because what we are going to do is to look at ln q and differentiate it with respect to beta and things like that, right? So when you do that, you will have terms that look like partial ln something that depends on 0 point energy by beta plus partial ln other things by beta. And the 0 point energy has no dependence on beta. So this term will just go to 0. So that's why we don't care about this 0 point energy, which comes in the prefactor. We just say, don't worry about it. It's something. We will just put it as 1. Okay. So with that explanation, let me write down the Q again. It is n1, n2 equal to 0 going to infinity e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus n3 epsilon 3 plus dot dot dot. Okay. And this we call as equation number 12, I guess, equation number 12. Okay, so we have our Q and we want to see with it, can we derive what is, we have a long way to go. We have to think about what is the energy density associated with a given frequency, and even more fundamental, given a frequency, we know that it can be in ground state, it can be in excited state, ES1, ES2, if everything was in ground state for that frequency, if all photons switch to ground state, then the average value of n, the occupation number for that frequency, is 0, right? And you expect that to happen at 0 temperature. But as you start exciting the system, some of them will move to an excited state, and the average value of n will now be more than 0. And we want to calculate how does this depend on temperature. And this was such an important problem. It was first derived by Planck, Max Planck, and it's called the Planck distribution. That's what we are going to derive next from this expression. So since it's so important, let me write down once again. We are doing n1, n2, dot, 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 equal to 0, infinity. Those of you who are pulling your hair, if you have someone like me, because of all this quantum mechanics, don't worry, the quantum mechanics will go down in a bit. You will have plenty of other reasons to pull your hair out for. It won't be quantum mechanics, it will be other things. I'm not saying it's going to get easy, but quantum mechanics is one aspect. So the bulk of statistical mechanics we have done. We have the tools. Now we are applying it to different problems. And the idea in taking such a course, this is not an undergraduate course, this is the graduate course. The idea in you taking such a course is that you see how tools are applied to different problems, so that when you go and do your research, you are all PhD students, which means some point in your life, you probably all thought or were told by your parents, one day you're going to win the Nobel Prize or something like that. So when you solve a problem that no one has ever solved before, you now have tools to look at it, and that tool is statistical mechanics. So that's the idea here. So I will never give you a problem in homework or exam which requires you to do some quantum mechanics. I will clarify anything that comes from the quantum mechanics to make your life easy. Still might be confusing, because quantum mechanics is confusing, and we will see how that works. So we have to write down Q, and this is going to be e to the power minus beta n1 epsilon 1 plus n2 epsilon 2 plus dot dot dot. So let's try to simplify this. How do we simplify this? This is a sum over exponentials, and this is something we have seen so many times. What we do with this is to write it as a product over j. So this is n1, n2, nj dot dot dot. So we say j goes from 1 to wherever, infinity, and the sum over exponentials now becomes product over sum. So this becomes then nj is equal to 0 to infinity e to the power minus beta nj epsilon j. if this is confusing, close your notes and derive until it is not confusing, because this manipulation is super powerful. We have shown it many, many times. The best way to work with it is to just, your hint is to just start with N1, N2, and then see how it works out. Then do it for N3, see it how it works out. Then we'll be like, aha, of course it's trivial. We have seen it at least 3 times so far. So we have this. So now this becomes product over J1 to infinity. And then we have our favorite geometric series, 1 plus e to the power minus beta epsilon j plus e to the power minus 2 beta epsilon j plus dot dot dot, right? This is a series we have summed. This is a geometric series where 1 plus x squared plus dot 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 gives us 1 by 1 minus x. And the only thing here is that x is equal to e to the power minus beta epsilon j. So we get this is equal to product over j 1 by 1 minus x. And what is x? X is e to the power minus beta epsilon j. Suddenly everything simplified, which is wonderful. We have q, right? So this is q, equation number 13. What we seek is, what is the average occupation number corresponding to a given frequency, right? What is the average occupation number for, and when I say frequency, that's interchangeable with energy, right? Because epsilon j is equal to h cut omega j. Why do I care about this? Because as I mentioned, at very, very low temperature, the occupation number for, as temperature goes to 0, you expect the occupation number to go to 0 because everything will be in ground state at T is equal to 0. And J increases more than 0 as T increases more than 0. And that's what we want to figure out, right? What is this number? Can we do something about it? Well, remember the first class in statistical mechanics, how do we calculate the average of anything? We go to every microstate, we look at whatever that quantity is going to be in that microstate and multiply by the probability of that microstate, right? So what is that going to be over here? We going to every microstate is again equivalent to going to different values of N1, N2, N3. And this is also kind of subtle. We are trying to calculate the average value of Nj, but we are summing over every microstate. You might say here, why do you care? Why are you trying to sum over N1, N2, N3? And you might be right. Maybe we could have done this by thinking only of Nj and not N1, N2, N3 for J not equal to 1, 2, 3, because the oscillators are independent. So that should work. But for now, let's do it in the full way. So this will be the value of Nj. What is Nj? Well, Nj in that microstate is Nj. It does not depend on N1. It does not depend on N3. It depends only on whatever value you have ascribed to Nj down here, right? So Nj, then the probability. What is the probability? It is e to the power minus beta N1 epsilon 1, N2 epsilon 2 plus dot 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 divided by Q, which we just calculated, right? We just calculated our Q. So, and we did Q, wrote down Q over here. So I keep calling my different tricks in StatMech as my #1 favorite trick, but it's kind of degenerate. They're all favorite. So this one, which is switching from sum to product, is one of my favorite tricks. Sum of an exponential series, a geometric series, is also one of my favorite tricks. But all of them are beat by the fact that you can calculate complicated averages by simply differentiating log of the partition function with respect to something else, right? And this is obvious from, let's call this as equation 13a and this as 13b. From 13a, if you go and look at 13a and you differentiate it with respect to beta epsilon j, if you differentiate with respect to beta epsilon 1, N1 will come out here, right? If you differentiate with respect to beta epsilon 2, N2 will come out here. And that's the idea. Let me remove that dot. So we just saw that average Nj is equal to partial ln q by minus differentiated with respect to minus beta epsilon j. So we are almost there. We are almost at the Planck's distribution. And this is page 7. So let's go to page 8. So we have shown that Q is equal to product over J 1 by 1 minus e to the power minus beta epsilon J. This already shows you this is a product of individual partition functions, right? Why did that happen? Because we said they are independent harmonic oscillators. So that's why you have a product. Epsilon J, epsilon 1 is completely independent of epsilon 2. So omega 1 is just multiplied with the partition function for omega 2. So note product form over here. This shows independence. Okay. And we have shown Nj is equal to partial ln q by partial minus beta epsilon j. So using both. Now, what is ln q? Ln q is summation j ln of 1 by 1 minus e to the power minus beta epsilon j. And since we are differentiating with respect to minus beta epsilon j, this summation just doesn't matter because all the other terms will not be differentiated. They will just fall out as a constant. We get Nj is equal to partial by partial minus beta epsilon j of, we can ignore the summation now altogether, and this will be minus ln of 1 minus e to the power minus beta epsilon j. We bring it to the numerator. And this becomes e to the power minus beta epsilon j by e to the power by 1 minus e to the power minus beta epsilon j, which is the same as e to the power beta epsilon j minus 1 whole to the power minus 1. Or we have just shown that the average occupation number for oscillator with frequency omega j, i.e. h cut, sorry, or epsilon j is equal to h cut omega j, these are two ways of writing it, is given by e to the power beta epsilon j minus 1 to the power minus 1. This distribution, which came after a bit of pain, but not too much, is super, super important. It's called, it's so important, its name is equation 14, but it's also called Planck's distribution. Max Planck was the first person to derive it. And you can look at its, I would like you to look at its limiting properties. Limiting properties as beta tends to 0 and beta tends to infinity. Homework without any grade, it's for your understanding. Also work through the math, but look at it, what happens to it at different temperature and does it not make sense? Later, when we do bosons, we will be doing bosons with a finite chemical potential. And then when we set mu is equal to 0, we will recover this formula. Next time what we are going to do, so what we have done so far is to talk about the average occupation number, right? So we have all these states, ground state, excited state 1, excited state 2, and we just talk about on an average, what will be the occupation number. We haven't yet talked about what is the probability of observing such a frequency, right? The g of omega is still unknown. So next time we are going to bring in a g of omega, which will again be omega square, but one crucial difference, we won't have a cutoff. When you were talking about lattice vibrations, we had a cutoff. For photons, you can have any frequency that you want. And then we will derive the full Stefan Boltzmann law. We are basically there, just a couple of lines of derivation. And next class, we will also look at bosons and fermions. Any questions? Okay, so I would like this Slack to be more active. I keep saying it, people don't do that. So my way of doing it is that I'm going to start asking questions to you there, okay? If you don't want you asking you questions, start asking me questions. So if you go and post questions on the questions for Prof channel, then you are free. I will not ask you questions. But if I see you not posting a question, I'm going to pick you and ask you a question over there. You can call me mean for that, but trust me, it will keep you engaged in the semester. It's not all the way done. We have a long way to go, and it's in everyone's interest that you stay engaged, at least to some level. So please, if because something must not, there must be some things that are not clear to you. I'm not that good of a teacher. Whatever is not clear to you, go and ask on the questions for the Prof channel, and I will try to help you explain it. If you don't ask me, then I will think, well, everything is clear to you, so I'm going to ask you questions. Okay, I think that's a fair deal. So I look forward to questions from you all. It will be helpful in improving our understanding together, because it's not just you learning. Every time I teach it, I also learn. So please ask me questions, and otherwise I will see you on Thursday, day after tomorrow.